In this video, I will explain how to train classification model. In many machine learning algorithms, we basically collect the data, which basically pair of input and output. But for the classification task, each output Y has some label information. Or, for instance, in the handwritten digit case, we have some class label for the handwritten digit. And then we have to define a model that can map from input to output. And we have to define a loss function to assess your model's output accuracy. And then we have to optimize the loss function. That is the training process of your model. Okay, but here in the classification task, since the output labels are not real number, usually, it is very hard to deal with, especially with your programming language. So for the qualitative variables, we usually define variables, output variables, as many as the number of classes, and then assign each variable to each class index. That is called one-hot vector encoding. So basically, we generate all zero vector except one non-zero having value 1 element, which corresponds to class label. Then every output labels have the same distance each other. Okay, there is no spatial relationship, or there is no ordering at all. So we can fairly compare the output labels. Right. For the classification task, we usually make the output estimation y hat using the same dimensional vector. And in many cases, we use some probability vector to fit your output one-hot vector, like this. Sum of entries is equal to 1, and all element values are non-negative. Okay, so which follows some probability property. And each element corresponding to the conditional distribution y equal to k for given your input x. Okay, so basically your model output y hat indicate the conditional probability for your each output label y. Okay, so there is constraint. Your sum of output label output values must be equal to 1, and each y hat k should be non-negative for all k. So here I will use capital K to denote the number of classes throughout this class. Right. This makes sense, right? To assess the accuracy we want to the both y and y hat follow the same rule. The rule is sum of entry must be equal to 1 and all the entries must be non-negative, right? But the problem is these two constraints actually make your algorithm harder. It is very, very difficult to design some learning process that satisfies some specific constraint. Okay? So many people use this special function, Softmax function, right? Instead of directly obtaining y hat vector from your model function, people usually first obtain some score vector, we'll call the logic vector. The dimension of the vector is the number of classes as before, and its value indicate the score of each class. And score means how much your input X looks like the class K. So here GKX indicate the score value. And then using this score vector, we learn some softmax function. We learn the softmax function using the G1 X to G capital K X, which make the output same dimensional vector with this form. Okay. Why this softmax function is very useful? Look, it is very easy to check the sum of entries is equal to 1. And also all the entries are positive because exponential function is a positive function, right? So usually we define a score vector first and then take softmax function so that our output can satisfy the two constraints in the previous slide. Okay, and one special example is the logistic regression, what we have in our textbook. Okay, so the logistic regression basically solve the case the capital K equal to 2. There are only two classes. Then we just need to G1 function and G2 function, right? And with one single input variable, so we just need to define a linear function for each score function with two coefficients for each, like a b1 beta 1 0 plus beta 1 1 x for the first score vector, beta 2 0 plus beta 2 1 x for the second score vector. And then learn softmax and then make a prediction using this softmax vector. Okay, the prediction, of course, find the index k that maximize this conditional property. But when you look at our textbook, you may notice that in the textbook we only use 2 coefficients. Essentially, in the square vector, the first element is usually. Let's look at the softmax function again. This function form is g1 x exponential g1x over some k is equal to 1 to capital K exponential zkx exponential g capital Kx over the same value. Okay. So when you divide by exponential g1x for every entry to the both numerator and denominator, all values will be the same because we divide by the same value to in numerator and denominator same time. Values never change, and which essentially equal to 1 over capital K exponential zkx minus g1x. Right? The second element value is exponential g2x minus g1x over sum k equal to 1 capital K exponential g k x minus g1x. So here, to define the vector, we just need to g2x minus g1x value, g3x minus g1x value, g capital Kx minus g1x value. So let's say this is equal to g2 prime x, this is equal to g3 prime x, this is equal to g capital K prime x. We just need to capital K minus 1 function. So when k is equal to capital K is equal to 2 for the binary classification task, we just need to define g prime 2x, which is equal to beta 0 plus beta 1 x in our textbook. So for the regression task, we just need to find the beta 0 and beta 1, right? Okay. So this is the definition of softmax and why softmax is useful for classification task. I explained this. Right. Then how can we define the loss function? Loss function is also very important for machine learning process. Since both y and y hat satisfy the same property, sum of entries equal to 1, and all the elements are non-negative, we can define the loss function in many different ways. As in regression task, we can define some loss function using this absolute error, or this square sum. Okay, but they already we discussed for the regression task, and they are not interesting loss function for classification task. For the classification task, minus log inner product between y and y hat is very important. This is very popular and have many nice properties. Essentially, this is negative log likelihood. Okay, so we usually define this negative log likelihood function for your training loss. So basically your loss function is sum over all training data point minus log yi, the true output label, and then y hat, which comes from your softmax output. That's it. Basically, the y hat comes from your training model or your model function, which is usually parameterized by some parameter. Okay. For instance, in your logistic regression case, this contains some parameter beta 0 and beta 1. Right, so this loss function is function of this parameter, and we want to optimize beta loss function with respect to beta 0 and beta 1. And when you minimize the loss function, basically you can have very nice parameter. That's it.